In this video, we're going to start chapter 8, and we're going to do probably sections 8.1 and 8.2 in the same video. There's really not much to say in 8.1. This is a major shift, or a start of a major shift in terms of our content, where if you think about what we've done so far here, is we spent a lot of time talking about probability and different probability distributions. We looked specifically at a whole chapter of discrete distributions, and then recently we looked at a whole chapter, of continuous distributions. And so what we're going to do in chapter 8 now, we actually will be getting the statistics proportion of this class. This is supposed to be an introduction to probability and statistics. And so everything that we're going to do from here on out is sort of in that realm of things, statistics. Now, probability questions will come up. They are obviously very closely related subjects, but this is the statistics portion if you wanted to sort of divvy up the content that way. So we have some brief introductions into the statistics realm way back when we originally started the semester. So we're just going to bring a few things back to the forefront in these as we start these sections. A population, we might remember, consists of the totality of all observations. Let's see, it looks like my pen just froze. There we go. A population consists of the totality of the observations. And a sample is a subset of the population. The sample is a subset of the population. Okay. And if we're going to do any sort of statistical inference, the sample is supposed to be representative of the population, ideally. Supposed to be representative of the population. And I'm not going to try to open up a whole can of worms there talking about representative samples. There's a whole class, survey sampling or statistical sampling, that is devoted to talking about choosing samples. There's a statistics course that our department offers at UMD. There's also survey sampling and marketing research courses that you can take, I believe, from the business school at UMD as well, that kind of addresses this issue. A lot of what we're going to do in terms of statistical inference here just sort of really relies on the idea that we have a random sample, okay? If you pick and choose the elements that are going to be in your sample and hand pick them, that for sure is not random, and you can guarantee that you're not going to be able to make a good representation of the population. So let's just consider maybe we are talking about a battery manufacturer. The population then includes all possible batteries produced by the manufacturer. The population includes all possible batteries produced by a manufacturer, produced by the manufacturer. All right. Now, suppose the lives of all of these batteries follow a normal distribution. The length of lifetime, the lifetime of the battery, the lives of all these batteries follow a normal distribution. Normal distribution f of x, normal distribution. Let's say we have a mean of 4 and a variance of 1. All right. And we will randomly select 8 batteries. We randomly select 8 of these batteries. Okay. And if we do this randomly, their lives, their individual lives, we'll say x sub 1 is the notation. So life of the second battery, x sub 2, so on and so forth. Life of the 8th battery in the sample, x sub 8, are independent random quantities. Independent random quantities. Independent random quantities. Now, each of these, pulling from the normal distribution, each of these is supposed to follow that population distribution. They all follow the population distribution. But they're independent random quantities because if, for example, the first battery dies in 1 year, that doesn't necessarily affect the probability that the second battery dies in 1 year, because these are all pulled at the same time at random. And so, just some notation here. We would say x1 follows a normal distribution. We will frequently use this little tilde symbol that's sort of taken the place of the word follow. x1 follows a normal distribution with a mean of 4 and a standard deviation of 1. x2 follows a normal distribution with a mean of 4 and a standard deviation of 1. So on and so forth. We would say all of these follow a normal distribution with a mean of 4 and a standard deviation of 1. Okay? All right. So really what we're doing here is we're just setting some things up, talking about populations and samples here, and setting some things up here for section 8.2, where we are going to talk about some of the statistics that you can get from these samples. The main goal in selecting random samples is to elicit information about the population. So typically, the population mean and variance are unknown, and that's the typical idea, right? So when I look at this right here, I know the population mean is 4 and the standard deviation is 1. And so if I take a random sample, then I know the distribution of each of those random items in the random sample. But typically you don't know what the mean of the population is. And so, if we didn't know that the mean was 4 and the standard deviation is 1, we could look at some statistics on the 8 selected batteries and get some ideas about the mean mu and the standard deviation sigma. Mu, this is how you would spell the letter mu. This is how you'd spell the Greek letter sigma. So we have a definition here in 8.2. Any function of the random variables constituting a random sample is a statistic. Remember, we use the word statistic to talk about a characterization of the sample. We would use the word parameter to talk about a characterization of the population. There are 2 general kinds of statistics that we're going to look at. 2 kinds of statistics. 2 kinds of statistics. One are statistics that are measures of location. Measures of location or measures of centrality. There's a variety of these that we can use in terms of statistics. They are we can look at the sample mean or sample average. You could look at the sample median. And we'll define what all of these are shortly. We could look at the sample mode, just to name a few. These are all measures of location. The second kind of statistic is a measure of variability. Measure of variability. So that is something like the sample variance. the sample variance, or the sample standard deviation. Or, here's a new one, the sample range. The sample range. So we're going to go through, let's define what some of these things are. You might have some previous experience with some of these statistics, but we're going to go ahead and treat these as a new topic here. And let's start out with some of the measures of location. Let's talk about the sample mean. The sample mean. So suppose the random sample consists of n random variables, x1, x2, yada yada yada, xn. Then the sample mean, also called the sample average, the sample mean, we denote this with x bar. X bar is calculated as follows. X bar is the sum of all of your x's as I goes from, we have n independent or n random variables, so I goes from 1 to n. Sum of all the xi's divided by n. So you add them up and divide by the number in your sample, right? So if we open up the sum, it would be x1 plus x2 plus x3, yada yada yada. We have xn. We add all of them up, and then we divide by n. Sample mean. Sample median. Sample median, given the observations, in a sample, x1, x2, yada yada, xn, are arranged in increasing order, increasing or ascending increasing order, the sample median is calculated as follows. Sample median, we have x tilde there for sample median. The sample median is, well, if you have an odd number in your sample, if n is odd, then it's just the middle element. If n is odd, then it would just be the middle element. So if you have 11 items in your sample, it is the 6th element because that leaves 5 to the left and 5 to the right. And so that would be x, if these are ordered in increasing order, that would be x sub n plus 1 over 2. If n is even, then it is 1/2 xn over 2 plus x n over 2 plus 1. And we'll take a look at an example with some numbers here. But if n is even, this is essentially the average of the two most middle numbers. Let's throw one more in here before we get to that example. The sample mode is very straightforward. Very direct, the sample mode. It's just the value of the sample that occurs most often. The value of the sample that occurs most often. Okay, so we got sample mean, sample median, and sample mode. Let's dive into this and see if we can't compute some of these. So let's suppose that we have a sample, and the sample is observations are 3.9, 2.2, 1.7, 3.9, 2.8, and 4.7. Let's go ahead and find the sample mean, median, and mode. Starting off with the mean, let's take a look at what we have here. So far we have a sample of, what do we got? 1, 2, 3, 4, 5. There's 6. N is equal to 6 in this case. There's 6, sample of 6. So x bar is equal to the sum of all of these divided by 6. So that is 3.9, 2.2 plus 1.7 plus 3.9 plus 2.8 plus 4.7 all over 6. So we run that through a calculator. And what do we get? 3.2. 3.2. That is the sample mean. Notice 3.2 is not actually one of the observed values, and that is A-OK. Much in the like we've had in our past probability distributions, the mean or expected value of a distribution there is oftentimes not an observed or possibly real observed value. 3.2 is the sample mean. Let's take a look next. How about the median? To find the median, we need to rank them in ascending order. We write our observations here, write them in increasing order. Write them in increasing order. Increasing order. So what do we have? Smallest observation is 1.7. Next up, 2.2. Then 2.8. Then 3.9. 3.9 occurs twice. And then 4.7. You do need to list that twice. We do need to list that twice. So again, these would be our observations: x1, x2, x3, x4, x5, and x6. We have 6 observations. This is even. And so what is the middle here? It's the average of your 2 middle values. So x tilde is the average, or 1/2 x3 plus x4. So that is the average of these. That is 2.8 plus 3.9 over 2. And right smack dab in the middle of those is 3.35. 3.35. Oh, last but not least, the sample mode. Well, I think it's pretty clear that 3.9 is the only observation that occurs twice. That one is the one that occurs most, so the mode is 3.9. 3.9. Sample mean, median, and mode. Let's talk about some variability measures on samples. Let's start out with the sample range, one of the simplest measures of variability. The sample range is just the difference between the largest and smallest values. Difference between the largest and smallest values in the sample. The book tends to use the letter capital R, and it says this is equal to x sub max minus x sub min, where x max is the largest value and x min is the smallest. So if we look at the previous question, the previous sample, what is the sample range? The largest value, we have it ordered right here to find the median, is 4.7. The smallest is 1.7, and so the sample range is 3. Sample range is 3. Sample variance. Sample variance. Sample variance is denoted S squared. S squared, this is very similar to the notation for the population variance, which is sigma squared. We have S squared, and this is given by the following definition, which is going to look very similar to the definition of population variance. We have a 1 over n minus 1 times the sum if we have n observations, I goes from 1 to n, of the difference of each of the xi's minus the sample average x bar squared. I would really encourage you to take a look and compare this definition of, well, this is the sample variance definition, to the original definition of the variance of a random variable. And that is something that you're talking way back in something like potentially chapters 3 or 4. Very similar sums in terms of like x minus mu squared. We have xi minus x bar, quantity squared. All things are in terms of the sample averages. And then we're dividing by this n minus 1 coefficient as well. The good news is that the sample standard deviation has the same relationship. The sample standard deviation, which is just S, because it is the square root of your sample variance S squared. It is the square root of your sample variance S squared. So similar idea with no good suggestive notation. The standard deviation is the square root of sigma squared, which is the variance. The sample standard deviation is the square root of the sample variance. Okay? And that is the definition of sample variance. Now, much like in terms of the original idea of the variance of a random variable, we had an alternative formula, an alternative definition to compute the variance of a random variable, which was the expected value of x squared minus the mean squared. We also have an alternative formulation to compute the sample variance. So this is the alternative formula for S squared. And this is stated as theorem 8.1 in the textbook. And this says that the sample variance S squared is 1 over n times n minus 1 times the quantity n times the sum from I equals 1 to n of the observations squared minus the sum as I goes from 1 to n of the observations, that quantity squared. And again, look at the similarities here between the alternative formulation for the variance of a random variable. It is very similar. I want to just go ahead and finish out then using the previous data we had. Let's calculate the sample variance. This might look worse initially than the original definition, but it's actually not so bad. It's actually not so bad, and it simply is, it's quite nice because in this alternative definition, you don't actually need x bar squared. You're doing much more addition and a lot less subtraction. There's one subtraction step here, whereas in the original definition, you're subtracting everything and then squaring it for each observation, and that can be cumbersome. So let's just do one last example in this video. We'll just continue from before with the data. Let me rewrite the data we had above. We had a 3.9, 2.2, 1.7, 3.9, 2.8, and 4.7. And 4.7. Okay, so let's go ahead and work through this. Let's see what we have here. So first, let's take a look at, we need the sum of all of the individual observations. So let's do the sum of all the xi's as I goes from 1 to 6. That's working on this component right there. Well, that's just adding them up. So we just add up 3.9 plus 2.2 plus 1.7, just add everything up. We should get 19.2, right? Good. Now over here, this is a little bit different, right? This is the sum of each of the observations squared now. So now we're looking at just this component. So the sum as I goes from 1 to 6 of each of the xi squared, we need to go through our calculator and do 3.9 squared plus 2.2 squared, right? This is 3.9 squared plus 2.2 squared, yada, 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 plus 4.7 squared, and add everything together there, we should get 68.08. And with those two pieces ready to go, finding s squared then is, well, relatively doable. Remember, what is n here? N is the sample size. N is 6. You have 6 sample points. 1, 2, 3, 4, 5, 6 numbers. So this is 1 over n times n minus 1. That is 6 times 5. N times the sum of the squares. 6 times 68.08 minus the square of the sums, minus 19.2 squared. And then we can just run that through the calculator and find the sample variance to be 1.328. 1.328. That would be your sample variance. And for good measure, while we're at it, let's just get the standard deviation, S. That's the square root then of 1.328, which we should find to be 1.152. All right. What I want to do in the next video, I'll cut this one here. In the next video, I do want to go through a proof, just for us to see that these are in fact equal. So in the next video, we will prove theorem 8.1, just so we know that we are allowed to use it with good right. Okay. See you in the next video.